Hi everybody, in this video I'm going to show you how to use the double angle identities, and we'll work a few problems together and verify a couple of identities together, and I'll start off by showing you where the identities came from. So here we go. We're going to use the sum identities to derive the double angle identity, so we'll start with the cosine. So we already knew the identity for cosine of a plus b. Now if you imagine that A and B are the same angle, then we could just use A for both of them. So let's go through and replace every B with an A. And now we have cosine of A plus A, which could be written as 2A. And then we have cosine times cosine, which is cosine squared, and sine times sine, which is sine squared. So we get a new identity for cosine of 2a. Now this would be helpful if you knew the value of the cosine and sine of one angle. You could use those two to find the cosine of double that angle. So, sometimes that does happen, so we could do that. But now, what if you didn't have both cosine and sine? What if you only had one or the other? Well, we can use a Pythagorean substitution to make this formula even better. So now we're going to start with that identity that we just derived, and let's remember that we had this Pythagorean identity that said sine squared plus cosine squared equals 1. If we isolate the sine squared term on the left side of the equal mark, then the right side will say 1 minus cosine squared. So that means over here, where the double angle identity has cosine squared minus sine squared, I can replace sine squared with 1 minus cosine squared. So let's do that. Okay, so we've replaced the sine squared a with 1 minus cosine squared a. And now we want to distribute this minus sign to these parentheses. Now the reason the parentheses are here is because sine squared a has been replaced by two terms. So if you're supposed to subtract sine squared a, you have to now subtract both of these terms. So we'll distribute that minus sign, and we'll get minus 1 and minus negative cosine squared, which is really plus cosine squared. Now combining like terms, 1 cosine squared a plus 1 cosine squared a makes 2 cosine squared a, and we end up with a new identity for cosine of 2a. We had cosine squared minus sine squared, but now we also have another formula, a second form of this identity. So cosine of 2a equals 2 cosine squared a minus 1. This way, if you only know cosine of a, you can still find cosine of twice a. So it's a good alternative formula. Now let's take that same Pythagorean identity, and instead of solving it for sine squared, let's solve it for cosine squared. So cosine squared is equal to 1 minus sine squared. That means over here in our original cosine of 2a identity, I can now replace cosine squared with 1 minus sine squared. See, we replace cosine squared a with 1 minus sine squared a. Now we can combine like terms. I have minus 1 sine squared and minus 1 sine squared, so together they make minus 2 sine squared. And that is a third form of that identity. Now all three of these forms are on your identity sheet, so you do not have to memorize them, but you should know that they are there so that you can use them when you need to. Alright, now let's also use the sum identity for sine to come up with a double angle identity for sine. So here is the sum of a plus, or the sine of a plus b, and if I again say that a equals b, so that both of these can be written as a, then we have sine of a plus a equals sine a cosine a plus cosine a times sine a. And now look, sine times cosine and cosine times sine are the same term. So we have the same term twice. So we can combine terms, and we now have sine of 2a equals 2 sine a times cosine a. So that is the only form of that identity. So sine of 2a equals 2 sine a cosine a, and that's also on your identity sheet. So now let's look at the tangent formula. If we start with the tangent of a plus b, and that's on our identity sheet, and we replace b, or substitute in place of b, the angle a, then we can have tangent of a plus tangent of a over 1 minus tangent a times tangent a. So in the top, tangent a plus tangent a is 2 tangent a, and in the bottom, tangent a times tangent a is tangent squared a. So we get 1 minus tangent squared a. There are all the identities that we've come up with so far for double angles. We have the 3 different forms of the cosine identity, and we have the sine of 2a and the tangent of 2a. Okay, now we'll walk through example 1 together. Given that cosine of theta equals 3/5 and sine of theta is less than 0, find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So when they say that sine of theta is less than 0, of course they're trying to tell you that sine of theta is negative. That gives us a clue as to the quadrant. If sine is negative but cosine is positive, then we have to be talking about an angle in quadrant 4. Now we'll start out by finding the sine of 2 theta, so let's first look at the sine of 2 theta identity and see what we have and what we don't have. Well, they did give us the cosine of theta in the problem, but they did not give us the sine of theta, so we'll have to find that on our own. Since cosine of theta is 3/5, we know the horizontal side is 5 and the hypotenuse, the horizontal side is 3 and the hypotenuse is 5, and the vertical side is 4. You can use the Pythagorean theorem to find that. So now, when we substitute into our identity, sine of theta is going to be negative 4/5 because we're in the 4th quadrant where sines are negative, and cosine is going to be 3/5, and we'll just multiply these together. 2 times negative 4 is negative 8, negative 8 times 3 is negative 24, and in the denominator 5 times 5 is 25. And let's look at the cosine of 2 theta. We may as well use the 2 cosine squared theta minus 1 form of the identity. You could actually use any form that you like, but since they gave us cosine in the problem, let's just use that one. So cosine of theta is 3/5. So when I replace cosine of theta with 3/5, remember to square it because in the formula it's squared. Alright, now 3 times 3 is 9, and 5 times 5 is 25, so that's the square of 3/5. Now multiply 2 times 9 is 18, and 1 is equivalent to 25/25, so that's just common denominators. 18 minus 25 is negative 7, and the denominator stays the same, so that's cosine. Now for tangent, we could use the tangent of 2 theta identity. So let's go ahead and do that. We can get from our diagram that the tangent of theta is negative 4/3. Remember, it's vertical over horizontal. And then the denominator would be 1 minus negative 4/3 squared. Okay, now in the top, 2 times negative 4/3 is negative 8/3. In the bottom, negative 4/3 squared is 16/9. So we have to do the squaring first. Negative times negative makes positive, and then this negative is still there. So that's why we have a minus here. So instead of doing this subtraction, I like to clear out the denominators. So I will pick the common denominator of these two little denominators is 9. And that means I have to multiply the top and the bottom by 9. So in the top, we're going to get negative 8 times 9/3. Now you simplify first. It's easier that way. 9 over 3 is 3, and negative 8 times 3 is going to be negative 24. In the bottom, 1 times 9 is 9, and with the second term, the 9's will cancel and we'll be left with negative 16. So we now have negative 24 over negative 7, which is positive 24 over 7. Or you can look at it this way. Since we already had found sine of 2 theta and cosine of 2 theta, you could take the quotient identity and say tangent of 2 theta is equal to sine of 2 theta over cosine of 2 theta. We already know both of those values, so substitute them in there. Then your two little denominators are 25, so multiply top and bottom by 25. The 25's will cancel, and you'll be left with still 24 over 27, just like before. This seems a little easier to me, but it was only possible because we had already done the hard work to find these two. So otherwise, these two together were probably more work than this one formula. But I want you to make connections and see your different options. So that's why we took a look at it both ways. For example 2, they're giving us cosine of 2 theta equals 4/5, and they're telling us that theta is between 90 and 180. So that means theta is in quadrant 2. And they're asking us to find the 6 trig functions of theta. Now, because they gave us the cosine of 2 theta, it makes me want to start with one of my cosine of 2 theta identities. So let's just use the 2 cosine squared theta minus 1. And that will allow us to find the cosine of theta first. So we'll substitute. The cosine of 2 theta was given to us as 4/5. And, oh, by the way, the reason I chose this identity instead of cosine squared minus sine squared is because I only need to have one unknown at a time. If you have two unknowns at a time, it's very difficult to solve. It's impossible. So I chose one where I only had one thing unknown. So now we've got cosine of 2 theta equals 4/5, and that's equal to 2 cosine squared theta minus 1. Okay, our job here is to isolate the cosine of theta. So we're going to have to start by adding 1 to both sides. Now 4/5 plus 1 would be 4/5 plus 5/5, which is 9/5. And that's going to be equal to 2 cosine squared. We need to divide both sides by 2. So if you divide the right side by 2, it cancels out the 2. If you divide the left side by 2, the 2 shows up in the denominator, and you get 9 over 10 equals cosine squared. Now you have to get rid of the square. So you have to do the square root of both sides. And when you do the square root of the right side, of course, it removes the square, but when you do the square root of the left side, it puts the whole thing under the radical. And whenever you do the square root of both sides of an equation, you have to insert that plus minus sign. So the square root of 9, well, before we do that, since we know theta is in quadrant 2, then we know cosine of theta is less than 0. So we don't have to really keep both of these signs. We know that cosine of theta in the second quadrant should be negative. So we'll just do away with the plus sign. Now, to simplify this radical, there is a quotient rule for radicals that says the square root of a fraction is equal to the square root of the top over the square root of the bottom. You just give the top and the bottom each their own radical. Now, of course, in the top, the square root of 9 is 3. And then we need to rationalize that denominator. So we end up with negative negative 3 times square root of 10 all over 10. Now that we know one function of theta and we know where theta is, we really can use that one function to find the other 5. You could still use the double angle identities again to find sine of theta, but we really have enough now to find it on our own. So I'm going to draw us a theta in quadrant 2, and we know from our unrationalized version of our cosine, which, you know, you could use either one, but why not use the unrationalized one because it's simpler. if this is cosine, then the horizontal side is 3, and the hypotenuse is square root of 10. And then we can find the vertical side by saying square root of 10 squared minus 3 squared, which would be 10 minus 9 is 1. So the vertical side is square root of 1. And now we can find all the other functions. So sine is going to be 1 over square root of 10. See, vertical over hypotenuse, which is going to rationalize to square root of 10 over 10. Tangent is going to be negative 1 over 3 because it's negative vertical over horizontal. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. And that's really probably the easiest way to find those three. You know, like I said, we could have used the double angle identity containing sine squared to find the sine, pretty similar to the way we did this. But since we already had the cosine of theta, this turned out to be just a little easier to do. Here's our first verify problem. We'll start out with cotangent of x times sine of 2x equals 1 plus cosine of 2x. And we have to decide which side to work with first. And I say, since there are 3 different forms of the cosine of 2x, and we don't know which one to use, let's not substitute over here because we might make a choice that makes our work harder. But instead, let's substitute things on the left side, because there's only one thing you can put in the place of sine of 2x, and there's only really one thing you can put in the place of cotangent. But there are 3 of these, so let's take a look at these 3, because you want to have these 3 identities in mind, because when you work with the left side and one of these identities pops up, you want to be able to recognize it. So cosine of 2 theta could be cosine squared minus sine squared, could be 2 cosine squared minus 1, or 1 minus 2 sine squared. Any one of these 3 will get the job done. So now let's go back to the left side, and we will replace cotangent of x with cosine over sine, and we will replace sine of 2x with 2 sine x cosine x, and that's because of our double angle identity. Now, because we have sine in the top and sine in the bottom, those will reduce, and we're left with 2 cosine squared x. Now, the 2 cosine squared x makes me think of this middle identity, which I've copied here. What I want to do with my identity is try to isolate that term that I have in my problem. Let's try to isolate that and see what it's equal to. So if we add 1 to both sides, we can see that 2 cosine squared theta equals cosine 2 theta plus 1. That means I can substitute cosine 2 theta plus 1 in place of what I had. I get cosine 2 theta, or 2x plus 1, and that's what my right side of my identity says. So now we can see that they really are the same. Okay, now let's try tangent of 2 theta equals negative 2 tangent theta over secant squared theta minus 1, or sorry, minus 2. Okay, for this one there are probably a couple of different things you could do. I would start off by noticing that the tangent of 2 theta, according to our 2 theta identity, is 2 tangent theta over 1 minus tangent squared theta. And look at what you have and compare it to what you want it to be. Notice that the top is already set except for the sine, but the bottom is very close, because we know that we have an identity that relates secant squared and tangent squared. We have that Pythagorean identity that says 1 plus tangent squared equals secant squared. So let's replace secant squared with tangent squared plus 1. So it was secant squared minus 2. Now it's tangent squared theta plus 1 minus 2. And we'll combine our like terms on the bottom. 1 minus 2 is going to leave us with negative 1. Okay, now this is where we are, And this is where we want to go, because if we can say that this expression is equal to this expression, then we can say that that's equal to tangent of 2 theta. So the only difference between what we have and what we want is that the top is the wrong sign and the bottom, the terms are backwards. Now look, we know the order of the terms is not important when you're adding, but you can see that the tangent squared theta term is positive here. We want it to be negative. The 1 is negative. We want it to be positive. The top is negative. We want it to be positive. So all the signs are wrong. If we will just multiply the top and the bottom by -1, multiplying by -1 changes the signs. If we do the bottom and the top by -1, then it doesn't change the value, it just changes the way it looks. So the top will become 2 tangent theta, and the bottom will become negative tangent squared theta plus 1, which we could write as 1 minus tangent squared, and that is equal to our double angle identity, so that is equal to tangent of 2 theta, and the job is done. Let's verify that 1 plus cosine of 2x, all divided by sine of 2x, equals cotangent of x. So the first thing I would do is get in my head all of the choices I have for cosine of 2x, and also take a look at the sine of 2x identity. And we just have to substitute these cosine of 2x identities out of the way. And I think if we are smart about how we substitute the cosine of 2x, we can get rid of this 1. Now look over here at your choices. This one contains a -1, and I like that because since my problem contains a +1, if I can substitute with an identity that contains a -1, then when we combine terms, that term will go away. So let's do that. And all the time we're thinking about how cotangent of x is equal to cosine over sine. So now in the top I've got 1 plus cosine 2x, so I've replaced the cosine of 2x with that identity that we picked out. And then in the bottom, sine of 2x becomes 2 sine x cosine x. Now go back to the top. Let's combine like terms in the top. +1 and -1 add up to 0. So the top becomes 2 cosine squared x, and the bottom becomes 2 sine x cosine x. So now we need to reduce. In the top I have cosine squared, and in the bottom I have cosine. So if I have 2 cosine factors in the top, one of them will be canceled by this bottom cosine factor, and it'll leave 1. Leave one of the cosines there. So that I've canceled out the second power, and in the bottom the cosine function, and then we will also cancel the 2's, and we're left in the end with cosine of x over sine of x, which is equal to cotangent of x according to our quotient identity, and that finishes the job. Okay, here's one more we can do together. Verify that cotangent of a minus tangent of a over cotangent of a plus tangent of a is equal to cosine of 2a. So again, I would start by looking at my cosine of 2 theta identities so that you know when you work on this, if you can make it look like one of these, you'll know that you've found the answer. And it doesn't matter which one, so it's like you have an even bigger target to hit. It's good that you have 3 to choose from, because whichever one you get to, you can use. Alright, now because we cannot actually combine these terms, it will be good if we use sines and cosines to rewrite this left side of this identity. So I've traded cotangent for cosine over sine, and I've traded tangent for sine over cosine in every place. Now, we want to simplify this complex fraction, and the way we do that is pick out the common denominator of all your little denominators, and that common denominator would be sine times cosine. So now you can actually distribute sine times cosine to each fraction. And so I've done cosine over sine times sine cosine, and sine over cosine times sine cosine, and in the bottom, same thing, cosine over sine times sine cosine, and sine over cosine times sine cosine. So just everywhere I've added a sine cosine to every term. Okay, what that does for us is it lets us simplify in a really neat way. Now these here in this first top left fraction, the sines are going to cancel and we're left with cosine times cosine, and here the cosines will cancel, and here the sines will cancel, and here the cosines will cancel. So let's see what that gives us. That leaves us with cosine squared minus sine squared, and in the bottom cosine squared plus sine squared, which we recognize as our Pythagorean identity. So now the top, see, is cosine squared minus sine squared, which is one of our identities. So the top becomes cosine of 2, well I wrote theta, but it should be A. Okay, and then the bottom becomes 1, and cosine of 2A over 1 reduces to cosine of 2A. And that finishes the job, because that's the other side of our identity.